and we can get back to it. Alrighty guys, so we are, I don't know, about halfway? I think we're about halfway through this last section of chapter 5. It's a big section. And the last thing that we did on Friday was we used the rational root theorem, remainder theorem, and synthetic division to figure out a zero of this cubic. And once we found a zero of this cubic, meaning one of its solutions, and we saw that that solution was x equals -1, we were able to use synthetic division to get us to this quadratic. And we're happy when we get to quadratics, if you remember, because quadratics always have two solutions, and we can solve every quadratic either using the quadratic formula if we're unlucky, or by factoring if we are lucky, because factoring's quick and painless. And this was one of those times where once we had our quadratic, we could factor. So we got 3 real solutions. They're not necessarily written in order. If I remember correctly, I did write them in order for you guys, and I think I accidentally switched the period 1 and period 3 packets. Whatever, the point is, there's your 3 solutions. Cool? Now, I don't think something I did was actually write the polynomial in its fully factored form. So we might as well write it factored, since we do know what the solutions are. And factors, are the sets of parentheses with the x's and crap inside of them. And since they're multiplied to each other, it doesn't matter what order you put them in. So that's unimportant. Okay? Don't get hung up on that. So in no particular order, I guess we'll say, where do I have space? I guess I'll squeeze it in right down here. That f of x from Friday was, and does yours say -2, -1, and then 1/2? Is that what yours says? It's the same answers, but I'll write them in the factors in that order, since that's the order that I wrote the solutions in. If x minus 2 is a solution, then we know that x plus 2 is a factor. If x minus 1 is a solution, then we know that x plus 1 is a factor. And then the last one. 1/2 is a solution, but x minus 1/2 is not the factor. And the reason why I know that minus 1/2 is not the factor, I can't write x minus 1/2 here, because if I come all the way up here, there's a 2 at the front, right? And there's a 2 at the back. Okay, well, the 2 at the front could be handled very easily. If you remember back to quadratics, anytime there's an a value, a multiplier, vertical stretch or shrink, it doesn't matter what form of the polynomial you write it in, a is still the same. So actually, there's a 2 right there. Okay, well, that solved the 2 at the front, but what about the 2 at the back? Imagine I wrote, don't write it please, imagine I wrote, and I'm going to do it in pencil so I can erase it, x minus 1/2. Don't do this, okay? If you were to FOIL all this out, you'd get 2 times 1, which is 2, and you'd get that 2 times this -1/2, which would be -1. And it probably wouldn't work out very well. So what's going to happen then? Well, oh, you know what I just realized? There's my quadratic factor. What am I doing? I'm working way too hard. There it is right there. I'll be okay. We factored it. Completely forgot. See, that's what happens when you do part of the question on Friday and try to finish it on Monday. Those were the 2 factors. So that 2 didn't need to be there. I'm just tired, I guess. It was x plus 2, x plus 1, and then the other one that the quadratic gave us was this 2x minus 1. There we go. I'll be okay. Much better. So this x equals 1/2 comes from this 2x minus 1. There we go. I'll be okay. So we have 3 linear factors. If the directions say to factor a polynomial, I'm looking for a setup like that. If the directions say to solve for the zeros or find the solutions or you find the x-intercept, anything like, I'm looking for answers like this. So solve, find solutions, find roots. That means tell me what x equals. Factor means get it broken down into as many small pieces as you can. Cool? At least with the difference between the two? Yeah? So let's do it again. We have another cubic, and cubics always have 3 solutions, right? Yes, Mr. Fantastic. Qubits are always going to have 3 solutions. If we could find one of those solutions, then we could use synthetic division to get us down to a quadratic just like we did on the example from Friday. And we want to do that because getting to quadratics is our bread and butter. We can solve quadratics by factoring if we're lucky, or quadratic formula if it's irreducible. So let's start hunting for possible answers. We'll begin with P over Q. And this time we're in luck because Q is 1. That means we don't have to do any fractions in our remainder theorem. Is that black pen? Let's get a separate that right there. Okay. That way we know that that's for the one above it. So P over Q. For P, we write out all of the positive and negative factors of 10. So plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. And like I said, Q is just 1, so we only have to check the numbers 1, 2, 5, and 10, positive and negative. And we don't have to check them all. We only need one to work. We find one that works using the remainder theorem, and we're thrilled, because then we can use synthetic division. Yes, Max? The 1, 2, and the 5 are all the factors of 10. See? P, P. So these numbers up here are all of the numbers you can divide this by. Positive and negative. And the numbers down here are all the numbers that you can divide this by. But there's only a 1 there, so 1 is the only thing that goes. Remainder theorem time. I always check x equals positive 1 first because it's the easiest number to check. And I always hope that positive 1 works. That doesn't mean it always does, but I always hope it does. Here I'm just writing out my polynomial with parentheses everywhere I'm going to substitute in a number. Come on, positive 1. Because if that works, it's an easy question. 1 cubed is 1. Negative 4 times 1 is negative 4. 9 times 1 is 9, and then minus 10. 1 and 9 makes 10. 10 minus 10 is 0, and 0 minus 4 is not 0. And 0 was the only number that would have made us happy. Since it's not 0, we know that x equals 1 is not a solution. Shucks. That's okay. The next number we're going to check is negative 1. So let's do it again. You know, something I didn't discuss with this question was Descartes' rule of sign. Could I use it? Sure I could. But I typically don't use Descartes' rule of sign for cubics because it ends up being work that wasn't worth the effort, to be honest with you. It still works. It holds true. I mean, look, let's see, 1, 2, 3 sign switches. There's either 3 or 1. Yeah, there's either 3 or 1 positive solutions. And if you wanted to, you could plug in negative x for all the x's. You know what? Let's do that real quick. What happens if you plug in negative x? If you remember the shortcut, remember what I told you is all it's going to do is switch the symbol that you have on anything with an odd exponent. Things with positive exponents stay exactly the same way they were. So here, I'm going to switch the symbol because that was an odd exponent. Here, even exponent, plugging in a negative does not affect it. Here, switch the symbol because odd exponent. Oh my goodness. Look at f of negative x. How many sign switches does it have? every one of these terms is negative. How many sign switches is that? 0 of them. Descartes' rule of sign actually helped us. It showed us there are no negative solutions. So I was about to plug in x equals -1. It won't work. Guaranteed. Descartes' rule of sign is showing me there are no negative solutions. Was it worth the effort? I don't know. That's a judgment call. I'll let you make that decision for yourself. You know what I mean? You could have checked -1. It wouldn't take too much work. You would have seen that it doesn't equal 0. But because Descartes' rule of sign has showed me no sign switches on f of -x, I am not going to plug in -1 for my next one. I'm not going to use any negative numbers. I'll just check the next smallest positive number. And let's see what we get. 2 to the third is 8. This is going to be 4, so I have -4 times 4. 9 times 2 is 18. 8 minus 16 is -8. And -8 plus 18 is 10. And 10 minus 10 is 0. We did it. Yay! We found a solution, which means we also know one of our factors. We know that x equals 2 is a solution. And we know that x minus 2 is a factor. That's a big deal. This was a cubic. Because we have one of its solutions, we can use that solution with synthetic division, and our result will be a quadratic, and we will either be able to factor that quadratic or we will not be able to factor that quadratic. If we can't factor it, it's irreducible. So to solve, we use the quadratic formula. Let's see. For synthetic division and for long division, make sure you're not missing any terms. X to the 3, 2, 1, none. We're not missing any terms. These are the coefficients of my polynomial. And we already know that the remainder is going to be 0. 2 worked. Guess what I got? A yellow pen. I'll use it sparingly because I know it's kind of hard to see, but I know the remainder is going to be 0. It's the small things in life. I bought it for myself for my birthday. Drop the 1 down and see what you get. 2 times 1 is 2. -4 plus 2 is -2. 2 times -2 is -4. 9 plus -4 is 5. And yep, 2 times 5 did get me the positive 10 that I was going to require to get that no remainder that we already knew was going to occur. These 3 numbers are the coefficients of our quadratic. We now have this quadratic factor. This quadratic factor, x squared minus 2x plus 5. So let me ask you, are there any 2 numbers that multiply to 5 that multiply to -2? Excuse me, that was stupid. Are there any 2 numbers that multiply to 5 that add to -2? There we go. More than one person shaking their head would be awesome. Okay, thank you, Amy. She shook her head, and Allie. Well, anyway, I got a bunch of silent people in the room today. No, there are no 2 numbers that multiply to 5 and add to -2. The significance of that is this doesn't factor. This is an irreducible quadratic. Our polynomial is fully factored when it is written in this format. This is as factored as it gets without using irrational or complex numbers. That's as good as it gets, because that's an irreducible quadratic. But we can still solve for x. Remember, the directions were to find all the zeros. That means all three solutions. We have one of them. We know one solution is x equals 0. And to find the others, we will set this irreducible quadratic equal to 0 and solve using the most powerful solver on the planet, at least for quadratics, quadratic formula. I always write my quadratic formula out. All right, negative. My b value is -2. Don't want to write too large because I'm running out of horizontal space over here. Plus or minus square root of b squared minus, get skinny math. Think thin thoughts. Let's see what that gets us. So again, this is factored. If the directions were to factor, that's your answer. And I keep saying that because I will be holding you accountable for knowing the difference between factoring and solving. On your test, you'll have some questions that say factor. On your test, you'll have some questions that say solve for x or find the zeros, or you just need to know the difference between the two. -2 is +2. And -4 squared is 4. But here, -4 times 1 times 5 is -20. Those guys are entertained, aren't they? So we have 2 plus or minus square root of -16. There we go. We have a square root of -16 in here. That means my other two solutions are complex. What's that square root of -16, folks? 4i. There we go. Square root of negative numbers is always imaginary. So the square root of -16 is 4i. And both of the numbers 2 and 4 can be divided by this denominator of 2. So we get our other two solutions are x equals 1 plus or minus 2i. Listing out all your solutions, since it does say what are all the zeros, we have x equals 2 and x equals 1 plus or minus 2i. That's all the zeros. That's factored. Those are the zeros.
The f of x one is factored.
So this is factored because this is irreducible. Yep. Factored just means break it down into all of its individual multipliers. Solve for x or find the zeros or find the solutions means what's going to make each one of those multipliers be equal to 0. And that's why we let this quadratic be equal to 0 to solve for it. So what's the big deal? Why make you know how to factor? The reason why you need to know how to factor as well as find the solutions is because the main goal of all of this is to turn these kinds of things into graphs. Spaghetti graphs, I like to call them. And if you flip the page, got yourself a wiggly graph. At the beginning of this lesson, a couple of videos ago, I introduced the word multiplicity to you. And the word multiplicity was what we used to describe a root that was repeated. So anything that happens more than one time, 2 or 3 or 4 or 5 more, times, rather than list an answer several times, we just say it has multiplicity. So it's repeated. We already know that. And I told you that that affects the graph somehow. At least it changes the way the graph behaves at that solution. Changes how we interact with the x-axis. Any answer, 0, x-intercept, that has odd multiplicity is going to make the graph behave like one of these two shapes. But both of these two shapes cross through the x-axis. So when you have an answer, x-intercept, solution, root, with an odd multiplicity, your graph is going to cross through the x-axis. Whereas a solution, root, 0, x-intercept, with an even multiplicity, like you see here, it's not going to cross through the x-axis, it's going to bounce off the x-axis at that number. And there's really only 3 shapes that these things can take on. So here we have 2 different shapes for odd. The part of the graph that you can still see. What kind of graph does this look like? Just the part you can see. What's it look like? It looks like a cubic, Daniel says, and he's right. It does look like a cubic. X to the 3rd. It behaves like a cubic. What that tells me is more than likely that solution has a multiplicity of 3. That factor would have a 3 written above its set of parentheses, more than likely. The part of the graph you can still see. What does it look like? Don't be afraid to say something obvious. It looks like a line, doesn't it? Yeah. Well, that tells me that more than likely that odd exponent is a 1. In fact, it's a guarantee. Because it passes through without any wiggling at all, it guarantees to me that the odd exponent was a 1. If it goes through wiggly like that, more than likely it's a 3, but it could be a 5, it could be a 7, but don't go nuts. If you hear hooves, don't wonder if it's a zebra, just assume it's a horse, okay, because that's more obvious. Go with the more obvious answer. It's probably a degree 3, probably a multiplicity of 3 there. This goes through like a straight line, so we say, yeah, it definitely has a power of 1 above its factor. You guys okay? Yeah? Okay. And the part of the graph you can still see, what is it shaped like? Come on, everybody in the room should know this. It looks like a parabola. And our parabolas are usually what degree? 2. Yeah. That's why even multiplicities bounce, because they behave like x squared graphs at their answer. They look like parabolas at the answer. So if you zoom in real close, like enhance, if you could zoom in and, the pinch and pull method like you would on your screen for a cell phone, you got really close, all you would see is a parabola. And that's how you bounce off of x-axis. Cool? So if we cross through the x-axis, we have 2 options. We're going to cross like a cubic, or we're going to cross like a line. Odd exponent on my factors. And if we're going to have an even exponent on the factor, we bounce. So let's sketch the graph of this polynomial. It's already factored for us, which is great. We don't have to do any rational root theorem. We don't have to do any remainder theorem. And we don't have to do any synthetic division. It's done for us. It's factored. And in the factored state that it is, we can see our solutions and we can see our multiplicities. That's going to tell us exactly how this graph behaves at its solutions. I am going to rewrite it though, just so I can draw arrows to point to its pieces. Remember, the order that you write these things factored is unimportant because the order of multiplication doesn't matter. But typically, if you have an x outside of parentheses, it's at the front. It's not wrong to put it between the 2 sets of parentheses. It's just weird. So right here, because this x is outside of the parentheses, what is its solution? Lots of people shouting out the answer would be awesome. X equals 0. It doesn't matter that there's a 2 there. That's unimportant. Because you're asking yourself, 2 times some number equals 0. I wonder what that number is. Clearly it's 0. But what is the exponent on that factor? It is a 1. It's not written, but it is a 1. And because it's a 1, that is an odd multiplicity. Which means it's going to cross through the x-axis at x equals 0. But because it's a 1, it's going to cross like a line. It won't get wiggly as it goes through it. It's just going to pass right through it. What is the solution from this factor? Lots of voices would be great. X equals what? Whoa, that was a mixed bag of answers. I don't think people were paying attention. Let's try again. Lots of voices. How many of you are there? There's 30 of you and you're all here today? No, I'm missing one person only? No, 2 people. So 28 voices, please. What does X equal here? Much better, -2. And the degree, the exponent, I keep saying degree. The exponent on this factor, is it even or odd? Odd. This number right here is an odd number. So this also has an odd multiplicity. And because we have an odd multiplicity, we know our graph is going to cross through the x-axis at the number x equals -2. However, because that odd number is a 3, our graph is going to behave like a cubic, which means it's going to get wiggly. Because it's an odd multiplicity, the graph is going to cross through the x-axis at that number. So I'm describing, because of the multiplicity, which is the exponent, how we're going to behave at that number. We're going to cross through the x-axis at that number. And we're going to do it as a wiggly cubic because the exponent was a 3. Yes, Gavin?
Does that mean would the -2 act as the function of the cubic?
Yeah, so his question, he asked me, does that mean the -2, not its origin, more its center? Yeah, so again, like if you just did like this, you could see, oh, I got a graph that looks somewhat like a cubic there. But you don't have to think about it like that, but at that number, just realize that your graph is going to change shape. That's what that means. And lastly, we have this solution. Let's do it over here because I have space. From this factor, lots of people, all 28 of you would be great. What does x equal here? Yay, 1. And the exponent on that factor, is it even or odd? Even. That means we have an even multiplicity. And all even multiplicities behave the same way. We're going to bounce off of the x-axis. I'll even put it in quotes. You're bouncing off the x-axis at x equals 1. So over here, I'm going to do a quick XY sketch. And I only care about 3 x values. They're the 3 that I wrote in red. X equals 1, x equals 0, and x equals -2. I'm trying to make it to scale. Earlier I graphed in purple and it didn't stand off very well. And my red and my orange look too similar. I've already used green, so I guess I'll graph in blue. I don't want to graph in yellow because the yellow is kind of hard to see. I only want to use it for very special occasions. So I'll graph in blue. I'm going to interact with the x-axis here, here, and here. There. Okay, that I know. That's where we interact with the x-axis. But I need to know one more important, vital piece of information before I can graph this thing. I need to know what the end behavior is, which is why we spent so much time learning about it last chapter. Now, period 1 struggled with this idea. If you were to FOIL this thing out right here, I'm going to write in yellow. If you FOIL this thing out right here, what would be at the beginning of its polynomial?
X squared.
X squared would be at its beginning. You can see that, right? Looks okay? Okay. And if you FOILed out this piece that you can see, what would be at the beginning of its polynomial? X cubed, x to the third. And at the front, you have a 2 and an x, and honestly, nobody cares about the 2. Not for what I'm talking about right now. If you multiply all 3 of those things together, what are you going to get? X to the 6th. Because remember, I wrote 6. Because remember, when you multiply numbers with the same base, you add their exponents. This tells us that our polynomial is degree 6. And we needed to know that because that's an even degree polynomial, which tells us something about our endings. So we know we have an even degree polynomial. What does that tell me about the endings since it's even? Use a word for it. Same or opposite? Same. Since it's an even degree polynomial, we know that our endings go the same direction. And the number at the front, the leading coefficient, the 2, is it positive or negative? It's positive. So since I have an even degree polynomial with a positive leading coefficient, what does it tell me about my endings? Which way do they point? Delaney? Both up. Yes, they both point up. Like that. Now we're ready to graph. We go back to our cheesy XY axis, and we know that we have this kind of scenario up at both of those zeros. Let's see, so like up here and up here, like that. And now, one at a time, we decide what the behavior was at each of its solutions. And I like to go from left to right. That's just what I do. Oh no, I dropped my blue pen. So I come over here to this x equals -2, and I see that I am going to cross through the x-axis like a cubic there. So it got wiggly at that number. Now something's going to have to happen because I have to come back up to here. So clearly I can't dip down forever. I am going to have to come back up to this because that's the next place I interact with the x-axis. So I don't know. That. You might be wondering how far down. And the answer is, who cares? Who knows? It's not important. You want to know how far down? I don't know. Plug in some numbers between 0 and -2. But please don't waste your time. Nobody cares. The point is you are going to have to come back up eventually to get to this x equals 0. Does that make sense? That's also why I didn't put any numbers on my y-axis, because we don't care. We're just getting the general shape in mind. That's all we're doing right now. Now that we're here at x equals 0, let's look back at behavior. At x equals 0, we are going to cross through the x-axis as if it was a line. So don't get wiggly. But clearly, I can't go up forever because I have to come back down here. I have to interact with this thing. And if you look at x equals 1, we were going to bounce off the x-axis like a parabola anyway. So it was going to be cup-shaped right there. So it was going to do this. How far up? I don't know. I don't care, and it doesn't matter. There it is. That's a general look at the shape of this graph. There was a lot of skills in this one question. And that didn't even involve us factoring it. So the actual questions are: solve for x using P over Q, remainder theorem, synthetic division, get it fully factored and solve. Then, once it's factored and you know all your x-intercepts, then you decide your end behavior and the behavior each of the zeros. Then you sketch the graph. That's all one question. When they're already factored, life is good. That's more than half of the work, in my opinion. Are there any questions I can answer about the skills that were in this question? The multiplicities, the behaviors, the degree, the end behavior, anything. Please ask me. I'm not interested in rushing a challenging lesson. No questions? Okay. I'd like for you to look at the box up above. Tell me what you notice. What's that? Yeah, it's the graph. It's just upside down. So this is basically this, just upside down. The only difference is, more than likely, this didn't have a 2 on the front of it. What did it have on the front? I don't remember. Something probably really small. Polynomials get really big really fast. But the point is, I could have written the equation of this graph just by looking at behavior and endings. Like this. I could see if x minus 2 is, or if x equals negative 2 is a solution, then I know x plus 2 is a factor. And because it's crossing through like a cubic, I would expect a third power. Because it crosses through the origin, I know x is a solution. And because it crosses through as a line, I expect and know that 1 is its power. And because x equals 1 is a solution, I know that x minus 1 is a factor. And because it bounces, it's shaped like a quadratic, that power is probably a 2. Could it be a 4 or a 6 or an 8? I mean, it could. It could. But it's probably a 2. Thinking horse, not zebra. And then, because my endings both point down, and these powers, 3 plus 1 plus 2, add up to 6, I know that there are no more x's. And because it points down, I know it's got a negative on the front. So I could have written this equation as y equals negative. Order doesn't matter, but it's weird to put an x between the parentheses. There you go. It can be that fast. And then you just have to hope that you never need to FOIL it all out, because that would just bite. All right. Skirt. So we're going to sketch the graph without going through the solving process again of this one. So we solved for x on Friday, and I touched on this one at the very beginning of the video / lesson and said we know that x plus 1 is a factor, and these are the other two factors. So this is its factored format. Normally, you would have had to gone through all the work of factoring said polynomial. But we already know what it factors to. We know it factors to was it x plus 2, x plus 1? X plus 2, x plus 1, and you can't see what I'm looking at, 2x minus 1. What are the exponents on those factors? They're all 1s. Every one of these factors has a power of 1. That means that my graph is going to behave like a line, a degree 1, at every one of its solutions. They're going to cross like lines at all 3 solutions. And those solutions were x equals negative 2, x equals negative 1, and x equals positive 1/2. That was all from Friday. And now that we know where it crosses the x-axis, and we've reviewed end behavior, and we know how it behaves at the x-axis, we can sketch this graph. What are the numbers? Negative 1, negative 2, and then 1/2. This is a degree 3 polynomial. So this is an odd degree. Odd degree polynomial tells me that my endings point different directions. They point opposite directions, with the front number being positive. So because it is an odd degree, they point different directions with a positive leading coefficient. That is an upwards overall graph, so it's going to behave like this. Left down, right up. That way it has an upwards trend overall. And we can sketch that now. So we're going to do this and this. But we know we're going to cross through every one of those x-intercepts as a line-ish thing. So don't get wiggly at the answer. There you go. Good enough. How far up, how far down? I don't know. Who cares? Not important. That is enough at least to know the shape of your graph. Appreciate you, nerds.